Okay, so last time we did pretty much the entire time talking about titration. We did a big sort of titration example. So remember at this point, we've talked about three different types of titrations: titration of a strong acid and a strong base, titration of a weak acid with a strong base, and a titration of a weak base with a strong acid. So you do need to be familiar with what those sort of titration curves look like. You do need to be familiar with, obviously, like we did in that example and a few other examples, be able to calculate correctly the pH anywhere along that titration curve. Remember that, as we talked about, pretty much, part of the battle is understanding sort of where you are in those curves. Because if you kind of know what type of titration, where you're at, you pretty much should kind of know what type of problem you should be doing even before you kind of pick up the pen or pencil to kind of do those problems. Um, the other good news, that we sort of talked about is that, really all the types of calculations that you do in titrations are really calculations that we've done before. So the key really is understanding when to do the calculations. So remember not to overlook things in your ice table that could kind of help you determine sort of where you're at, what you should be doing. And again, like the normal sort of stuff, because obviously in a titration, we're continuously adding volume. You want to always make sure you do that first table in moles. Then afterwards, always very, very good idea to convert those guys back to molarity at the end of that first ice table. Um, any questions about titrations or any of those type of calculations we've been talking about? Okay, so just to kind of finish up on the sort of titration topic here. Obviously, when we do titrations, we oftentimes obviously add indicator. And as we spoke about earlier on, the purpose of the indicator is obviously to give the person that's doing the titration a visual reference of, hey, you should probably stop your titration at this point. Usually, what we use the indicator for is obviously to determine if we've reached the equivalence point. In most sort of titrations that we do, oftentimes that is the ultimate goal, is to reach the equivalence point. Unlike some that we do in this class where we go past the equivalence point. But in sort of a normal titration, that's sort of your goal, is to get to that equivalence point. So what do we want in an indicator? How does an indicator sort of work? Well, really an indicator is pretty much a kind of like a weak acid. There's a IN, here's the indicator. There's really a protonated form, kind of like an acid, and there's kind of like a deprotonated form where the proton comes off, kind of like the base. So kind of like a weak acid conjugate base system is what's set up when you put sort of an indicator into your solution. Now, depending on sort of the ratio that you have of, sort of the acid part to the base part of the rate of the indicator, if that's greater than or equal to sort of 10, what we see in the solution is pretty much the color of the indicator in sort of acidic conditions. Opposite of that is sort of less than 10, that ratio. We see sort of the base color, if you will, sort of predominating in it. So they do work over a pH range, really. They work over this sort of pH range, whatever it may be. So we talked a number of times about, say, phenolphthalein, which is a common indicator. It's the one that kind of turns pink. It works like 8.3 to like 10-ish or so. And again, at the 8.3 level there, it's almost colorless. Yeah. And then again, it gradually sort of turns pink as you're going this way to really dark pink, at this end of the spectrum. And when you use an indicator like that, which is probably, if you've done a titration before, probably the indicator that you probably have used, the purpose of it, when people tell you, hey, you want to sort of stop your titration when you see that first like pink color, like so light pink that you got to put up like a piece of paper underneath it to kind of see the pink even that's there. A nice white piece of paper so you can kind of see the tinge of pink. And the reason they tell you to do that is because obviously if you sort of stop at that point, you're probably in this area, in the 8-ish range. And if you were doing that titration, you were probably doing maybe a titration of like vinegar and sodium hydroxide, which is a common titration people do. And what that means is you're probably at the equivalence point, because the equivalence point should be basic at that point. So that's also why it's important to understand what we've talked about in terms of the different types of titrations, what you're titrating, what happens at the equivalence point. Because if you do a titration of a strong acid, strong base, as we talked about, you would expect the equivalence point to be 7. So you wouldn't necessarily want maybe something that turns past 7. You want something that when you reach the equivalence point, you will actually see an actual color change, not just, it stays one color. So you're looking for really an indicator that changes color near the end point. So that's how you could kind of choose a proper indicator, is one that will change color near the equivalence point. And that's obviously equivalence point pH. So, we talked about that at the equivalence point, we could have a neutral sort of solution. At the equivalence point, we could have a basic solution. At the equivalence point, we could have an acidic solution. And that's why if you look here, pH is on the bottom. We got some acidic sort of indicators that change color in that sort of acidic range. We got some of these basic ones here, right, that sort of change color in that basic range. We got some in sort of around the 7-ish range as well. So in selecting an indicator is really important to make sure that you choose one that you can visually see the color change, when it happens and it's near the equivalence point. So for example, here, crystal violet is kind of a yellowish color in its acidic range, if you will. And as it goes down to here, it's blue. So this would be great, if we had something that had an equivalence point, in that range, or we're looking for a change. Again, you'd be able to see it go from kind of like a yellowish to a greenish color, or maybe even from the green to the blue color. You could also use it for a little further down the road as well. So, you're looking for one where you can visually see that color change. Here's phenolphthalein down here. Again, you can see most of it is really colorless. Then you get this tinge of pink, a little darker pink, and then super dark pink. And again, we use that kind of first shine of pink because you'll be, perhaps in this range. Any questions on indicators? So take a second. Here's a list of some indicators. And again, they're different colors in the sort of acidic or basic range for which they work, and decide, which one would be a good choice for this titration of HNO2 nitrous acid with potassium hydroxide. So take a moment and think about which ones from that list would be a good choice. Okay, so looking at this, first off, you would want to really determine what you're dealing with. So hopefully, I think we may be seeing this guy up around the road. That is actually a weak acid. That KOH is a strong base. So what does that mean? We're doing a titration of a weak acid with a strong base. And again, based on our conversations, we should have sort of maybe a visual in our head of, what we're dealing with. We got a titration curve that looks like this: volume of base, pH, equivalence point, say here. And we should know in this still, the pH should be basic. Again, it's going to be basic because it's going to create that salt at the equivalence point, right? The salt's going to go through hydrolysis. It's going to produce hydroxide, which will make it basic. So what does that mean? Well, it pretty much eliminates this one as it works over a range of 1.2 to 2.8. At about 2.8, we're done, obviously, with any type of color change. Same thing here, same thing here. Really, same thing here, same thing here. That's not going to really help us because, again, it should be basic. Now, this one here, you may say, well, it kind of dips gently into the basic range there at 7.6. But remember, that's sort of the end of the change, if you will. So probably in most cases, remember, you're going to kind of see a change in the color happening, as you're moving down. If you're kind of at the end, probably the color has already been changed way before that, which means that's not going to be very helpful visually for you to determine, you're at the equivalence point. So that one probably wouldn't be a good choice. This one right here, which is creosol red, goes from 7.2 to 8.8. So that could be a good choice, as obviously in that range, we'll see some type of change in terms of the color as we go from 7.2 to 8.8. And obviously phenolphthalein here would also be a good choice. So out of that list, perhaps suitable for this titration would be cresol red and phenolphthalein. And that's because of the type of titration we're doing and what we would expect to occur here at the equivalence point. Any questions on that? You could obviously, if you kind of know your setup of your titration, you know the molarities of everybody, or most of them, you could probably make a pretty educated guess roughly, you know, what the pH should be at the equivalence point, and also really narrow it in on a more and more specific sort of indicator. Any questions on indicators, how to choose the proper ones? Okay. All right, so that sort of wraps up titrations. So here we're going to talk about a couple more equilibrium type of expressions, because, you know, we don't have enough K values. So this is going to be about Ksp and Kf. So what we're going to talk about here, these two equilibrium sort of expressions, and we're going to talk about each of them individually. But basically, this one has to do with solubility, and this one has to do with what are known as complex ions. So we could add them to our ever-growing list of K values, are Ka, Kb, Kw, Kc, Kp, Ksp, you know, Kf. So, you know, like we talked about at the beginning, we're going to hit pretty much every K that's known to man here in this class. So let's first talk about sort of what Ksp is and sort of what the deal is with Ksp. Well, Ksp is really for things that are insoluble. Right. So when we deal with Ksp, what we're really dealing with are a lot of things that are typically, when we think about them, insoluble. And what does that has to do with? That has to do with obviously solubility rules. So perhaps in your last class, you went over solubility rules, I would imagine. It may be a good idea to refresh yourself on some of those solubility rules. It may be helpful here with this material. Not necessarily critical, I would say. You could probably still reasonably be able to figure out everything, you know, even if you maybe don't have a 100% handle on all the solubility rules. But again, refreshing yourself would probably be very helpful as well as we go through it. So when we look at something like silver chloride, which based on solubility rules tells us it's going to be insoluble. Chlorides are soluble in everything except for silver, lead, and mercury 1. And in this case, because it's hooked up with silver, it's a solid. So what does that mean? That means that it's going to be insoluble, but something that, you know, you maybe have been told before in the previous class is, hey, it's always going to be insoluble no matter what. And as we will learn here in this sort of topic here about Ksp, that's not always the case. So there's a couple of things that's important to remember, that even though when we look at something that is technically considered insoluble based on obviously solubility rules, everything has some degree of solubility, maybe super small, but there's some degree of solubility that does occur. So even something like silver chloride, that technically speaking, when we look at it in a beaker or a test tube or whatever it may be, looks completely solid to us, there is some degree of equilibrium happening. And that's what we see here in this equation. There's some degree of this silver chloride that, you know, will break apart into silver ions and chloride ions. And it will have a back and forth sort of equilibrium that occurs. So even though technically, you know, we've been sort of beat into our heads at this point probably that, hey, it's always soluble no matter what happens, you put those two things together, you're going to see a solid. That's not always the case. So most of the time you probably will see a solid, but there's a lot of conditions that can affect whether or not you actually do see that solid form. And we're going to talk about that. Things like concentration, things like pH of the solution have a very, very big effect on whether or not you actually will sort of see, the appearance of that solid. So because it really does set up this equilibrium, we can write a equilibrium constant expression for it. And we would do it the same way as we normally would. So this would be our products divided by our reactants, just like we normally do. But there is a slight difference when we deal with sort of Ksp, and it is on the reactant side. When you write these equations or sort of see these equations, it is always solid on the left-hand side, goes to basically aqueous ions on the right-hand side, your positive ion and your negative ion, basically. So what does that mean? That means when we write these sort of equilibrium expressions, we pretty much never have reactants in there because they are solids. And just like a normal, equilibrium constant, we don't include solids. So if we write this, this would be known as a Ksp, would be the concentration of silver times the concentration of chloride. Again here, because this guy is a solid, we do not include it. What does Ksp stand for? Sp stands for solubility product, and that's basically what it refers to. So as odd as it may sound, we have a whole table, a whole list, as we will see very shortly, of equilibrium constants for things that are typically insoluble and things that are typically solids. So this is a hint as well. When you see a Ksp sort of value or expression, you can probably safely assume that the reactant side is going to be a solid and the product side will be these aqueous ions. Now we see some other things here like magnesium fluoride. We also have silver carbonate, calcium phosphate. So remember, when these guys break apart, they don't always break apart into a 1-to-1 relationship in terms of their ions. There's a 1-to-2, a 2-to-1, a 3-to-2. So even though it's a little bit sort of different in the sense of no reactants, it is still an equilibrium constant, which means we still need to take those coefficients into account. So it's really important as well to understand how these ionic compounds break apart so that you again do get the correct sort of Ksp expression with the exponent that's there. Any questions on that there? And again, you can see that that is essentially the sort of setup always for Ksp sort of reactions: solid on the left, break it apart into the appropriate balanced ions on the right. You could write your Ksp expression for both of them. So how do we know if we are actually going to sort of get a solid to occur or not to occur? And one way that we could look at that, and we'll see a little bit more later on with some calculations, but one way we could actually determine whether or not we get a precipitate is actually using another sort of calculation that we've seen before, and that is Q. And if you remember, Q is the reaction quotient. We saw it when we talked about equilibrium originally. Q is calculated exactly just like you would calculate K, right? Q is basically calculated the same as K, calculated. So Q is calculated really the same as K, which means here in these sort of Ksp expressions, Q would also be just the products. So we could kind of do the same thing, set up Q on one side, set up K on the other side, and we could determine if Q is less than the Ksp, it will become an unsaturated solution. So just like we did with Q originally, you could kind of go the opposite way where that's pointing. So if we go the opposite way, that is pointing to aqueous ions, which tells us no precipitate will form. And that's what an unsaturated solution means. If you remember, an unsaturated solution is a solution where you have not really hit what is referred to as the saturation point. That means that, if you have more solid, it will continue to dissolve. it would really continue to dissolve until we kind of hit the next situation, which is Q is equal to the Ksp, and that would be a saturated solution. What is a saturated solution? A saturated solution is one where you pretty much have hit at a given temperature the maximum amount of solute or solid that will dissolve in a given amount of solvent. So, you got the unsaturated solution will continue to dissolve solid, no solid being formed. Then you hit pretty much your saturation point at your saturated solution. And that's sort of your tipping point right there. That's the point where, we pretty much hit maximum. Our jar is full, right? Where you can't put any more stuff in there. At that point, we kind of tip over to the other side and we get Q is greater than the Ksp. Again, if you just go opposite of where that's pointing, that takes us to the right-hand side of the sort of reaction. Right-hand side of the reaction is always a solid. So when Q is greater than the Ksp, we create what is known as a supersaturated solution. If you remember, perhaps a supersaturated solution is really a solution where you have kind of too much solid dissolved in a solvent, and it's not very happy in that situation. So it will pretty much break apart. And I'm not break apart, it will pretty much have the solid come out of solution, and you basically will make a precipitate. So we can use this value that we've seen earlier and calculates kind of the same way as well to determine whether or not, if we mix two things together, would we expect, a solid to form? And we'll do some calculations involving that a little bit later on here. Any questions on that so far?
Can you explain one more time why in unsaturated solutions there's no precipitate?
Yeah, so that's basically kind of what the definition of an unsaturated solution is. That basically, if you add more solid, it will basically dissolve. And it's because at a given temperature, there's a certain amount of, say, grams of any sort of solid, if you will, that you could get to dissolve in so much, say, volume of water, for example, water being like the solvent, this being like the solute. And for any sort of substance, there's a certain amount that you could get to dissolve, and it is based on temperature. And when we do have an unsaturated solution, what that means is we pretty much haven't hit that point yet. So let's just say, for example, that the maximum amount that we could dissolve of some type of solid was, say, 5 grams in 100 grams of water, right? So if we put 2 grams of that solid in 100 grams of water, we have no problem. It will dissolve right away. We put 3 grams, it will dissolve right away. This is still what is referred to as an unsaturated solution because we haven't hit that magical number, and it is different for different things of, how much we could kind of get to dissolve. We get to 4 grams, we're still an unsaturated solution because we could continue to dissolve until we hit 5 grams in this example. At that 5 gram mark, that is now becomes a saturated solution. So you could kind of think about it like, hey, I'm putting so much solid into this jar, right? Okay, I haven't fully saturated it or filled it up yet, so it's unsaturated. I can still fit more in, I can still fit more in, still fit more in, until you get to the very, very top, right? And I get to the very, very top, that would be sort of like you just hit your saturation point or saturated solution. If you want to throw more solid in there, right, it's going to start falling out, right? Because there's no room for it. And that would be kind of like when we start to see a precipitate form where we hit that saturated point, and then it's kind of like a tipping point. And that's the point where we would start to see solid form. So that's basically kind of the definition of unsaturated. It is, you really haven't hit that point of where you will see a solid form yet, because you have enough really solvent there, like water, to kind of handle it, dissolve it, take it in. But at some point, you're going to hit that point where you're out of room basically for the water to kind of grab up all that stuff. And that's really what happens when you dissolve something, right? Is it doesn't really disappear. Water comes in and grabs it, right? And grabs it, and you can't see it. It's kind of disappears in that sense, but it's really not gone. It's still there. It's just kind of wrapped around with a bunch of waters. But there at some point, depending on how much water you have in there, how much solid you have in there, you may run out of enough waters to kind of grab up everything. It's kind of like the old example of, you take sugar, right? take some sugar packets and, a couple of sugar packets, mix in water, it will dissolve. But if you're bored waiting for your food or whatever at a restaurant and you had like a big giant thing of sugar and you just dumped it in, at some point you could stir as much as you want, but you're just going to start piling up, right? Sugar and stuff on the bottom. It's going to stop dissolving. And that's because you've gone past the saturation point. Other questions on that? Okay, so this is a Ksp table. You have a similar one in your book. And there's a couple of things we should talk about in terms of on this table. And those couple of things are what the actual values we see. Not necessarily we have to memorize any of these numbers, but if you kind of scan over this table or a table in your book or any sort of Ksp table, you will see several things. And the most important thing that you'll see is that the Ksp values are very small. So what does a small Ksp value really mean? Well, because a Ksp is really an equilibrium constant, that means that basically we have a small value of K. And what does a small value of K means? It means that when we think about a reaction that's going from reactants to products, it means when we reach equilibrium, we mainly have reactants, right? Because it's small. When we think about a Ksp type of reaction, on the reactant side is always solid to our aqueous ions on the product side. That means if we just kind of tie all that together, small Ksp value means small K value. Small K value means we mainly have reactants when we reach equilibrium. Because of these type of reactions, that means we mainly have solids. So what does that mean? That is what we were just talking about, that for the most part, Ksp is the equilibrium constant for things that are insoluble. So that's why they're very small values. That's why most of the time when we see these things, we think of them as solids. We see them as solids because of that small value of equilibrium. Means that most of the time the equilibrium is hanging out on the reactant side. Any questions on that there? Okay, so then let's get into some calculations that are oftentimes done in these type of problems. And the first thing oftentimes, we sometimes want to find what is referred to as the molar solubility. And the molar solubility basically is the number of moles of a solute. Remember, a solution is basically two things, just to remind everybody. When we talk about a solution, there's two parts to it. There's the solute, which is the smaller part. And that's usually the thing that is dissolved, and the larger part, which is the solvent, which is the larger part. So for example, if you had a sodium chloride solution, sodium chloride would be your solute. Your solvent would most likely be water, right? So when we talk about the molar solubility, that's the moles per liter. Moles per liter is the molarity, right? So we basically find the molarity of a solution, which will basically tell us how many moles of that solute will dissolve in 1 liter of that solution. We also sometimes just ask about the regular sort of solubility, which is a more sort of useful number in the sense of if we were doing some type of experiment, and that is basically how many grams we could get to dissolve of that solute in 1 liter of saturated solution. And that's why we see G over L, which is how many grams per liter basically we could get to dissolve. To be honest with you, in Ksp problems, there's really two paths that you can take. One path is sort of the top one here. They give you the molar solubility sometimes. And from that, you can find the molar solubility of each of the ions, or the concentration of each of the ions. You then can stick it into the Ksp expression and actually solve for the Ksp. So this would be a problem where you're kind of trying to find the Ksp. Like that's sort of the goal, is to find the Ksp. The second sort of pathway is what we see on the bottom, where they give you a Ksp value, and that's pretty much it. They don't give you numbers. They don't give you anything else. They just give you the Ksp value. And in this case, you do need to really do an ice table. So it will involve an ice table sort of calculation. We're going to talk about how it's slightly different than some of the ones we've done before. And from that, that will allow you to get the molar solubility. It will also allow you to, if you wanted to, figure out the grams per liter. By the way, if we have moles per liter and we wanted to get ourselves to how many grams per liter, hopefully we know the one that allows us to do that is the molar mass, right? So the molar mass of the substance, which is grams per mole, is the one that will allow us to kind of go back and forth, really. So if we have moles per liter of a substance and we multiply by the molar mass, moles will cancel, leaving us with grams per liter. So we oftentimes will have to use the molar mass in some of these problems because, again, some of them may ask you about how many grams per liter can you kind of get. So this is sort of the pathway. The top one, in reality, you don't necessarily need to use an ice table. You can, it may help you sort of understand the calculation a little better, but you don't necessarily have to use the ice table. The bottom one, you do have to kind of use the ice table when you're doing that sort of pathway. So let us talk about this one here, and let's actually go through an example here together so that we hopefully understand what we're looking at here. So let's start with this one, which is the solubility of silver phosphate at 25 degrees is 1.6 times 10 to the minus 5 moles per liter. We want to know really what is the Ksp value. So I'm going to be honest with you, you probably don't actually need to do an ice table on this one, but I'm going to show you what the ice table looks like so that, again, hopefully you'll better understand the sort of the calculation part of it, but also help you when you do need to do an ice table. So the first thing we want to know is, obviously, if we're doing anything with Ksp, we do know a couple of things. We can pretty safely know this guy is a solid, yeah, because Ksp, again, is for things that are insoluble. So we would want to set up like an ice table like we normally would. The deal here, though, is we're just simply going to take our ionic compound and we're going to break it apart. Now, when we break it apart, we want to make sure we break it apart appropriately, which means this guy does break apart into 3 silvers and 1 phosphate ion. So again, very important, obviously, because we do need to use these coefficients in our Ksp expression, that we do write it sort of correctly. Any questions on how that breaks apart? So the Ksp expression, speaking of that, would be, again, our products over our reactants. Here, like we anticipate, our reactants is going to be a solid. So it will be our silver. And again, why that 3 is important, we do need to cube it because of the coefficient, just like we do with the normal kind of K, and times phosphate. And obviously that is what we're looking for here. All right, so once we sort of have this set up here, we can do an ice table. And you may be saying to yourself, wait a sec, there's like no kind of number to use here in our ice table. And you're right, there is a number, but we're not going to use a number in this calculation. So first off, this guy is solid, which means you don't have to worry about him, right? Because solid is not included in anything, so you should leave it alone. Initially, what you would assume in this case is we have nothing of these guys. So initially, we would assume 0 of our product side. What would our change be? Our change would normally be minus x, right? Plus x is on the right-hand side. When we do Ksp problems, we actually will a lot of times not use x. You could use x if you really wanted to, but a lot of times people don't use x. People use another letter. They use the letter S. And what does S represent? S represents what is known as the molar solubility, which is basically the molarity. So we do it the same way as we would with X. We still need to take the coefficient into account, which is important. So this would be 3S plus 3S. Again, 3 for the coefficient, S for the molar solubility. And this coefficient is 1, so this would be plus S. Bringing us to equilibrium here, again, not worrying about this guy because he's solid all the way through, giving us 3S and S. Any questions on that there? Now, if this was a problem where they actually did give you the Ksp, you would do just like we normally would do at this point, which is we would take those values and put it into our Ksp expression, which would be 3s square cubed, because of the cube here, times s. So what we did is basically just take both of these guys and put them in to the appropriate spots into that expression. Now, if this was a problem where we did have the Ksp and that was all we were given, we would do the same thing that we normally would do. We would actually solve for S. And what would S tell us? S would tell us the molar solubility. In this particular case, we actually have the molar solubility given to us. So this value right here is actually the molar solubility. And that's basically what S equals, which is 1.6 times 10 to the minus 5 molar, which means that is what we could just slap into here at this point, which would be 3 times 1.6 times 10 to the minus 5. We want to make sure we cube it times 1.6 times 10 to the minus 5. And if we do all that carefully, 3 times 1.6 to the minus 5, we're then going to cube it and then times it by 1.6 to the minus 5. That gives us something in the ballpark of 1.8 times 10 to the minus 18 as our Ksp value. Any questions on that? Now, that is how we kind of work ice tables when we're doing Ksp problems. And again, as I mentioned earlier, if the only thing you're given is the Ksp value and nothing else, you definitely have to do an ice table. When I say here in this particular problem, you actually don't necessarily need to do an ice table. What I mean by that is if you understand concentration and the relationship to the ions in an ionic compound, you would understand that when you look at something like this, and they gave you that the concentration of the whole thing is this number. If I wanted the concentration of the silver, it would be 3 times that number, right? Because it breaks apart into a 1 to 3 relationship, which would give me 3 times 1.6 to the minus 5. Gives me like 4.8 times 10 to the minus 5. It's a 1-to-1 relationship between the phosphate and the whole thing, which gives me 1.6. That is essentially what we just put into this expression here. You could then take these numbers like we just talked about and go right into here. It's really the same thing. Now, the benefit maybe of doing the ice table is not making a mistake that a lot of people make when they do this. And it kind of helps you look at it and sort of visually see, okay, I visually see that I need to, in this particular case, multiply it by 3 and then also cube it. It's a very common thing. People, when they do these problems, go, okay, I multiplied it by 3. Do I still need to cube it or not cube it? And that sometimes happens if people jump from here into here and you don't do it correctly. You forget to multiply it by 3 or you forget to cube it. So it's a very common thing that, sometimes people think like, wait, I'm doing it too many times. Like I multiplied it by 3. Now I'm also cubing it. That seems wrong. So, sometimes just doing the ice table, even though technically you didn't need to do it in this particular example, can kind of walk you through, should you be multiplying it and also cubing it or not? But you could technically, like I said, kind of just jump from the bottom here right into here and get the same answer as we got there. Any questions on how to kind of do the ice table or the calculation? And what did we see in terms of our answer? Well, we see a small value of Ksp, which is what we expect since this thing is mostly insoluble. Any questions on that one there? All right, now that I tried one, why don't you try one here? What is the Solubility of silver chloride in grams per liter. And let me give you a couple of pieces of information that might be helpful. First off, silver from the periodic table, 107.9 grams per mole. Chlorine from the periodic table, 35.45 grams per mole. And the Ksp value there for silver chloride is 1.6 times 10 to the minus 10. So take a few minutes here and see what you come up with. I'll give you a hint. We're only given the Ksp value here, which automatically means you need to do an ICE table. So see how you work through that and see what you come up with. Look and kind of see how you're doing. So first off, again, in a problem where you're pretty much only given the Ksp value, no other piece of information, that automatically should scream to you that you do need to do an ICE table for sure. So what is the ICE table really going to be sort of based upon? It is going to be based upon our solid guy here, which in this case is silver chloride. And we're just going to simply take our solid and break it apart into the appropriate ions, which in this case would be the silver ion plus the chloride ion. If we wrote our Ksp expression for this, the Ksp would equal the concentration of silver times the concentration of chloride, and that would equal our Ksp value, which in this case was the only real piece of information given to us. Again, we would set up our ICE table like we did before. We're going to ignore the solid, so we don't try to use a number where we shouldn't. We're always going to assume in most cases that we're starting with 0 of our ions. As it starts to break apart, we will again get plus S and plus S. Again, each coefficient is 1 there, so that's why it's just S for each of them. That bringing us down would get us to S and S at this point. Any questions on the ICE table here? Now, like a kind of normal equilibrium problem, at this point, we're going to take both of these values here, our letters, and we're basically going to substitute it into our Ksp expression. That means that the Ksp would equal basically S times S, which is S squared. That is 1.6 times 10 to the minus 10. That gives us S squared. To get us to S, we're going to take the square root of the other side, and that would end up giving us the square root of 1.6 to the minus 10. Going to give us a 1.3 to the minus 5, looks like. Now, what does this S represent? It obviously represents the S's in our table. It also represents the molar solubility. And what does it represent the molar solubility of? It represents really the concentration of silver ions that's in that solution at this point. It represents the concentration of chloride ions in that solution at the point. And it also represents the molar solubility of silver chloride. And you may be saying, well, how does it relate back to this guy? Whenever you solve for S in these sort of tables, it really is the molar solubility of the whole thing. Because if you just think about it, and we kind of went backwards. So for example, here, if we said, all right, I'm going to plug that number back into here. So that means that for my silver ions, it's 1.3 times 10 to the minus 5 moles per liter of silver ions. Now, when I do stoichiometry, it's a 1-to-1 relationship between those two, which means if I did the longhand stoichiometry here, 1 mole of silver ions gives me 1 mole of the entire thing, which means that the molarity of the entire thing is also, as you can see, 1.3 times 10 to the minus 5 moles per liter of silver chloride. So although you can do the stoichiometry back to get there, it usually is what S is the molar solubility of the whole thing, because you actually do take the mole to mole relationship into account here. So you would have that number down there and allow you to figure it out. Any questions on that there? So what does that mean? That's close to what we're looking for. That's the molar solubility, but remember, we're looking for grams per liter. So basically what we have at this point is 1.3 times 10 to the minus 5 moles per liter of silver chloride. Getting the molar mass of silver chloride is a silver ion that was 107.9, chlorine, which was 3545, giving us a grand total for a molar mass of what we got there, 143.4 grams per mole, we'll call it, I think. We will use that really as a conversion factor. Here, we're going to multiply by that number, 143.4 grams per mole of silver chloride from the periodic table. Moles will cancel, and that will tell us that the solubility here of silver chloride is 0.00, we'll call it 19, 0019 grams per liter. Any questions on that calculation there? So what does that mean? That number means something, right? That number means that if you have silver chloride and you put it in water, you could get to dissolve 0.0019 grams per every 1,000 milliliters of water. That's not very much, right? And that's why we normally consider silver chloride to be a solid, right? Because obviously you can see by this number, you could dissolve 0.00, basically 2 grams, which is not a lot, in 1,000 milliliters of water or 1 liter of water. And again, that's why we typically think of it as being insoluble. Any questions on that one there? All right, let's try another one here. We'll calculate the concentration of aluminum in this saturated solution of aluminum hydroxide, Ksp for aluminum hydroxide, 2 times 10 to the minus 32 at 25 degrees Celsius. Temperature not really important in the calculation, to be honest with you. So take a moment here and see what you come up with, and we'll talk about it. Okay, so let's take a look. So same approach here. A couple of things we could get just from the problem. Obviously, we're only given really the Ksp. That implies, obviously, we need an ice table. Also implies this guy's going to be really a solid. So we got aluminum hydroxide. Again, we want to make sure that we do break it apart properly. So that would give us 1 aluminum and 3 hydroxides. Again, we could write our Ksp expression here, which would be our products, which is our aluminum times our hydroxide cubed, and that would equal the value they gave us, 2 times 10 to the minus 32. Again, in this situation, no numbers given to you or anything, just the Ksp value, or you need to look up the Ksp value sometimes, means we're going to ice table this. So this can be 0 and 0. Change again going to be plus S and plus 3S, ignoring our solid over here so we don't try to use it in the inappropriate way, leaving us with S and 3S in terms of our ice table. Any questions on the ice table there? That then means that we're going to put this into our Ksp expression, and that S times 3S. And again, we want to make sure that we do cube it. Again, we're putting it into this expression here, each of those guys. That will equal our 2 times 10 to the minus 32. That is going to give us 27 S to the 4th is equal to 2 times 10 to the minus 32. I will say is a very common move that people cube the S, but forget to cube the 3. So remember, that's how we get the 27. 3 times 3 is 9, and 9 times 3 is 27. So you got to make sure, don't forget to cube the number. That's a very common mistake that people make. Dividing the 27 to the other side, giving us 2, nope, I'll try that again, 2 to the 32 divided by 27. That's going to give us 7.4 times 10 to the minus 34. At this point, we want to take the 4th root of that guy. So that's going to be something like, and I'll put in scientific notation so none of us count zeros, an S value of 5.2 times 10 to the minus 9. If you didn't put in scientific notation, you might have a bunch of zeros and a 5 at the end of your calculator, which works. By the way, just to make sure everybody kind of knows how to do this calculation, which is what we just did. Oops, minus 34. Again, you may have an actual calculator button that has that, so you obviously could hit that. Or if you want, what you could do is take the number, hit your kind of, mine is like X to the something, or maybe a caret type button, and do parentheses 1 divided by 4. So basically you're doing 7.4 times 10 to the minus 34 to 1 divided by 4. 1 divided by 4 is basically the fourth root. 1 divided by 2 is the square root. 1 divided by 3 is the cube root. So that's the way you can kind of do that. Kind of get that guy up there and do that. And I'll get you the fourth root for you on your calculator in case you maybe don't have that button or not sure how to use that button, like a caret or a button that kind of looks like that. Any questions on that there? So going back to our table, we see that S is what Al3 equals. So that would be the concentration of aluminum ions in our solution at that point, 5.2 times 10 to the minus 9. We do want to put molar because it is a concentration. Any questions on that problem there? Now, in addition, it didn't ask us, but we could also get our hydroxide concentration, by the way. Our hydroxide concentration would be a little different. As we could see, it actually equals, this guy equals S. This guy equals 3S, which means if we want the hydroxide concentration, we would have to multiply that number by 3. And that would get us 1.6 times 10 to the minus 8 molar. Any questions on that? So we could use this, obviously, as you can see, it does give us the concentration of each of the ions at equilibrium, but it will be also, when we get S, is also the molar solubility of the whole thing as well. And again, that 3 that we did here would come out if we went stoichiometry backwards to this guy, and it would work out the same. Also, since we have the hydroxide concentration in a value like this, we could also find something like pH as well, because we could find POH, and then we could find the pH of the solution from that value. So, you know, there's a little bit of some different applications that can happen here. Any questions on Ksp, kind of straightforward Ksp type problems? Okay, so it's just a table of some of the different relationships, you know, that you get when you, you know, got kind of 1 ion to 1 ion, 2 ions to 2 ions. So let's talk though about, can we use the Ksp values from the table, for example, to determine, you know, is something going to be more soluble than something else? Is there a salt that's going to be more soluble than something other than that? And the answer is yes and no. So what I mean by that is, if you are comparing several salts that break apart into the same number of ions, you can use the Ksp values directly from the table to compare which one would be more soluble, which one would be least soluble. So for example, if we look at silver iodide, when silver iodide breaks apart, you get a silver ion and an iodide ion. When copper 1 iodide breaks apart, you get a copper ion and an iodide ion. When calcium sulfate breaks apart, you get a calcium ion and a sulfate ion. And each of these, we basically end up with 2 ions. 2 ions basically means, if you kind of like do the the Ksp table like we just did, you're going to end up with S squared in each of the cases. So it's kind of like a constant, if you will. So what that means is you can directly look at the Ksp values and determine which one would be more soluble. So what would that actually tell you? So if you think about the setup here, as we talked about, of the reaction, solid on the left, aqueous ions on the right. If you compare the Ksp value and the one that has the smallest Ksp value, what would that mean? Out of that group, the one with the smallest Ksp value would be hanging out over here, which means it's going to be the most insoluble, right? It's going to be more solid than aqueous ions. The one that has the larger Ksp value means more products, which means it would be hanging out on that side and would be more soluble. So if you did a comparison of the Ksp values, you would find that the one that is most soluble is actually the one with the higher Ksp value. The one with the smaller Ksp value would be the one that is least insoluble because of that. So I don't have the numbers in front of me, but if we looked at the table in comparison of Ksp of calcium sulfate to, say, silver iodide, we would most likely find calcium sulfate having the larger Ksp value, meaning it is more soluble, and the silver iodide, meaning it is least soluble in this group. Why would that be important? Well, if you had like a mixture of some of these things, you can figure out a way to take out ions from the solution by precipitating them out by using the differences in Ksp values. So one rule is you can use the Ksp values to figure out which one is more soluble and which one is least soluble, but you can only do it in a specific sort of combination where you're comparing sort of apples to apples. They both, two things, three things, whatever you're comparing, they all break apart into the same number of ions. It has to be the same ions, but the same actual total number of ions, like 2, 2, 3 and 3, 4 and 4, whatever it may be, you know, they break apart into that. So what happens if we are looking at something that really doesn't break apart into the same number of ions? So if we look at an example here with some actual values, we can kind of see what happens. We have copper 2 sulfate there, which when it breaks apart, we get a copper 2 and a sulfate, or sulfide, sorry. When we have silver sulfide, I'll get that sulfate out of my head here. We get 2 silver ions and a sulfide. And we have our Bi2S3. Again, when it breaks apart, we get 2 of these guys here and 3 of these guys here. So in this case, we got somebody that has 2 ions. We got somebody here with 3 ions. And we got somebody here with a lot more than that, 5 ions. So in a situation where you're comparing things that break apart into multiple numbers of ions, you cannot use the Ksp value directly. So let's see why we can't do that. Well, if we look at these 3 guys and their Ksp values, and we just went solely based on the Ksp values, we would see that this guy here is the largest, and this guy is the smallest in terms of Ksp values, which if we were going to make our prediction based off of that, we would predict that, again, this guy on top being the largest Ksp value would be mostly products, and this guy would be the most soluble, while this guy being the smallest would be the least soluble. Our prediction. Now, when you actually do the calculation, just like we did a moment ago and calculated the actual solubility of each of these guys, what we actually see is the opposite. We actually see that the copper 2 sulfide is the least soluble. And actually here, the bismuth guy there is the most soluble. Remember, when you're looking at negative exponents, the smaller the negative number, the larger it is. So actually, the solubility is actually the opposite in order. And that is why when you are comparing things that do not break apart into the same number of ions, you should never use the Ksp values to do that. You do actually have to do a calculation like we just did to figure out, you know, which one would be more soluble and which one would be least soluble. Any questions on that there? All right, so now that we've talked about solubility, Ksp, and calculating these things, we're now going to talk about some things that do affect solubility. And again, these are some of the things that can affect whether or not we would expect to see a solid formed or not see a solid form. So the first thing that really can affect a whether or not we see a solid being formed is something that we saw when we talked about buffers, and that is what is referred to as the common ion effect. So as we saw with buffers and things of that nature, when we do have a common ion present, it will decrease the solubility of a salt, and it will also decrease the acid, for example, from breaking apart. How does that work in this case? Well, if we think about the Ksp sort of setup here, remember we have solid on the left-hand side of the arrow. We have aqueous ions on the right-hand side of the arrow, which means if we had a common ion, that would mean that we have some product. And our good friend Le Chatelier's principle tells us it would then cause the equilibrium to shift to the left-hand side. And when it shifts to the left-hand side, obviously now we would have more solid. More solid would decrease the solubility. So the presence of this common ion does exactly what it kind of does in the buffer situation. It forces that equilibrium, in this case, to the left. And in this case, on the left-hand side of all these sort of reactions are solids. And that means that we are going to be decreasing the solubility. Any questions on that? So let's take a look at an example here between silver bromide in just pure water and what happens if we put that silver bromide in a solution that contains sodium bromide. Let's start with just the pure water by itself. So if we had silver bromide in pure water, the Ksp would be our silver times our bromide, and that would come from our reaction here of this guy breaking apart into silver plus the bromide. Again, we have just the Ksp given to us, so we're going to do 0 and 0. Change is going to be plus S and plus S, which means at equilibrium, S and S. Going into our Ksp expression like we did before, that would get us S squared is equal to the Ksp value. Taking the square root of the other side there will get us square root of 7.7 to the minus 13. Looks like it gets us something like 8.8 to the minus 7. And that would be the molar solubility of silver bromide in water. Any questions on that calculation? That's essentially the same calculation as we've just been doing. Now, what happens if we stick this guy not into water, but into sodium bromide? So first off, sodium bromide, which is just a salt, is going to, when it goes for a swim in water, break apart into sodium ion and the bromide ion here. It is clearly the bromide ion, which is our common ion in this particular case. The concentration of the sodium bromide was 0.001 molar. It's a 1-to-1 relationship, which means 0.001 molar here. And what that means is if we set up our ice table here, silver bromide, just like we did before, going to our silver plus our bromide. And we go initially, we would have 0 here, but because the common ion is present, This guy for the bromide would not be 0. It would be 0.001. Rest of the ice table will be similar, plus S, which means at equilibrium S 0.001 plus S. Just like we've done before, we're going to put that into our expression, and that would get us S times 0.001 plus S is equal to our Ksp value of 7.7 times 10 to the minus 13. Again, at this point, what I'm doing is putting it into our Ksp expression like we did on the other side. What can we do at this point? Well, what we could do at this point is we don't want to do a lot of calculations, right? So this is definitely a small value of K for sure, like most Ksp values will be. And what that means is I can assume, much like I assume X is equal to 0, that S will equal 0. You obviously can't get rid of all the S's or you got nothing to solve for, but just the S, much like we do with the X that we add to something or subtract from something, will give us 0.001 times S as we multiply it over equals 7.7 times 10 to the minus 13, giving us an S value of 7.7 times 10 to the minus 10. We should check it like we normally do. We would divide that by 0.001, times it by 100, and we're nowhere even near 1%. So the check is good. Most cases, it probably will be good for this, guys. So what does that mean? That means that the molar solubility of silver bromide in sodium bromide is 7.7, all right, here, 7.7 times 10 to the minus 10 molar. What do we see upon comparison of our silver bromide in water versus our common ion of sodium bromide? Well, we see that again, it's 8.8 times 10 to the minus 7 molar. This guy is 7.7 times 10 to the minus 10 molar. We see that in sodium bromide, it is less soluble. It is less soluble because of the presence of that common ion to begin with, causing this equilibrium to be pushed back this way towards the reactant side and the solid. Question on any part of that there? Okay, so now that I tried one, why don't you try one and see what you come up with? What is the what would be the solubility of this compound in a solution that is potassium chromate, 0.1 molar potassium chromate? So what is our silver chromate's molar solubility? We'll go with molar solubility is good, I think. Why not? Actually, let's do both. Why not? Let's do, just to make sure, let's do molar solubility. And let's do grams per liter. So I'm going to give you some numbers that will be helpful. Silver is 107.9. Chromium is 57. And oxygen is 16. So take a few minutes here. We're looking for the molar solubility and the solubility in grams per liter in this common ion type problem. Again, pretty much given just Ksp, we are given a concentration of another solution. That's silver chromate, that's potassium chromate. So again, we're going to have that sort of common ion presence. This is the Ksp guy, so that is really where we would want to set up our ice table from. We also know it's going to be a solid because there's a Ksp value associated with it. When it breaks apart, it's going to be 2 silvers plus a chromate here. And the Ksp expression would be our product, so that's going to be our silver, which would get squared, times our chromate. And we do have a Ksp value of 9 times 10 to the minus 12. We do have 0.1 molar potassium chromate, Potassium chromate is K2CrO4. That's going to break apart into 2 potassiums and 1 chromate. And again, if you understand sort of molarities, when we look at potassium chromate to really the chromate, which is what we're interested in here, it is a 1-to-1 relationship, which means the chromate is 0.1 molar as well. The potassium would be a 1-to-2 relationship, so you would have to multiply the 0.1 times 2 if you're interested in potassium. In this case, we're not really interested in potassium. We're actually interested in our chromate, as it is the common ion here. So we're going to use that in our ICE table. And again, we're going to use it because that means initially we do have 0 of the silver, but this potassium chromate is supplying 0.1 molar of this guy. Change would be plus 2s again because of the 2, and plus s here. That means at equilibrium, we end up with 2s and 0.1 plus s. Any questions on the ICE table so far? All right, so just like we've been doing at this point, we're going to take what we got here, kind of similar to how we solve for x, and basically put it into here to solve for x. And if we do that, we will end up with 2s. Again, don't forget we do need to square it. Times 0.1 plus s would equal our Ksp value of 9 times 10 to the minus 12. Again, obviously 9 times 10 to the minus 12 is a very, very small value. We're going to assume s is equal to 0 like we just did a minute ago. Again, the s that we're adding it to. That's going to leave us with here 4s squared, taking care of this guy, times 0.1 is equal to 9 times 10 to the minus 12. Cleaning up the left-hand side there, 4 times 0.1 gives me 0.4. Oops, come here. 0.4, and that is s squared is equal to 9 times 10 to the minus 12. We're going to divide that to the other side. I'm also going to take the square root of it at the same time. So 9 to the minus 12 divided by 0.4. Now taking a square root of it, looks like we end up with something of 4.7 for s times 10 to the minus 6. And that would be the molar solubility of the silver chromate here in that solution. Any questions on that there? Now, when we do that, that's moles per liter. So we do want to convert it into, that would take care of the molar solubility. We now want to convert it into obviously grams per liter. So that is where our molar mass would come into play. So it looks like if we add up all those parts there, we got 2 silvers at 107.9 plus a chromium at 57 plus 4 oxygens at 16 each. Looks like the molar mass is 336.8 grams per mole. So converting this here from moles per liter of silver chromate. Using our molar mass here, we're going to multiply by 336.8 grams per mole. Moles will cancel. Times 4.7 to the minus 6 is, I'll go up here with it, 0.0016 grams per liter would be our solubility of silver chromate in this solution. That obviously is not a lot either. That means, again, you could take out, in this solution, you could get 0.0016 grams to dissolve in 1,000 milliliters of water. Again, due to the presence of that common ion, is going to decrease the solubility to where it was with water. Question on that calculation there. Okay, we will stop here for today in terms of